Google Cloud Data Flow is a unified and fully managed service for big data processing. Its goal is to reduce the time, cost, and complexity of answering big data questions. Cloud Data Flow can be used for traditional batch, aka MapReduce processing like ETL, and computation over arbitrarily large at-rest data. It can also be used to drive real-time analysis over high-throughput data streams. The unification of batch and stream processing reduces the development and operational complexity by enabling developers to focus on a single programming model and a common service environment. As a fully managed service, Cloud Data Flow provides automated work life cycle management, dynamic work optimization, intelligent auto-scaling, and integrated monitoring, freeing developers and administrators from the burden of allocating, deploying, optimizing, and managing compute and storage resources. Let's look at an example of where you might use Cloud Data Flow. This demo is based on a mobile music scenario where devices report back user actions like what song did they pick to play, and playback events like how long did it take for a song to start playing. This demo models 1 million users driving approximately 2,000 to 20,000 events per second depending on current usage cycle, addressing 4 different use cases. Specifically, I wanted to reliably ingest all of the raw event data into my database or data warehouse in real time. I want to have my raw event data available for interactive analysis. Secondly, I wanted to calculate the total active users of the system on a per minute basis in real time. Third, I wanted to calculate the total active users of the system on a per minute basis over historical data. And finally, I wanted to calculate some play suggestions in real time over historical data. To answer these questions, a developer would build a data flow pipeline using the data flow SDK to express their desired computation requirements. Here is the sample code for this demo. I have a pipeline with several branches. We will review some specifics of the code later in the demo. For now, let's get a job running. To start a job, you simply execute the pipeline. The data flow SDK will optimize your pipeline graph and submit the optimized graph to the service. The service will then spin up the needed compute and storage resources to execute the job and then start scheduling work. In this case, I am running a stream-based job, reading a continuous data stream from Cloud PubSub. The mobile devices forward events to a Cloud PubSub topic. This topic is globally available and can provide throughput of tens of thousands of events per second. Once a job is submitted to the service, you can view its overall health and processing throughput via Dataflow's integrated monitoring UI. You will notice that this job structure logically maps to the pipeline code, making it easy for developers and administrators to understand the logical execution behavior of the job versus dealing with lower level compute and resource metrics. Right now, the pipeline is processing roughly 5,000 events per second. The archive transform represents the code I wrote to address some ETL needs for the raw input events. My code then uses Dataflow's BigQuery sync to reliably write all the events to my dataset in BigQuery. BigQuery is a fully managed interactive analysis service capable of processing queries over petabytes of data. It's also capable of ingesting data at 100,000 rows per second per table. Here's a sampling query over the most recent 1 minute of mobile event data. The overall latency is roughly around 2 seconds. This data is instantly queryable. We solved problem 1. Let's move on to problem number 2. Problem number 2 was focused on continuous computation of active users on a per minute basis. To answer this question, I used Dataflow's powerful windowing primitives. Specifically, I used a fixed 1 minute window that effectively groups all of my data into a discrete time dimension. From there, my code does some processing to calculate user counts over event data. I'm writing the windowed output to BigQuery. Let's take a look at that output. This table contains all of the windowed session output. The start and end times represent the boundaries for the fixed window. You can see that there are a little over 162,000 active users in the system for the last fixed window. We answered problem number 2. Problem number 3 is a variant of problem number 2. We want to calculate active users over historical at-rest data versus a stream source. Typically, a developer would rewrite this as a batch-style question in MapReduce and then run it alongside the stream-based implementation. Dataflow's unified API enables seamless transitioning from stream to batch and batch to stream. Here's the code that I submitted for the streaming job. I'm going to change the input source to point to at-rest data on Google Cloud Storage, and I'm going to tell the pipeline to run in batch mode. Now I simply re-execute the pipeline, and we're now processing historical data. Keep in mind that my existing streaming pipeline is unaffected. Same code, same processing model, and batch and stream. We solved problem number 3.
Eric showed us how to stream data into BigQuery with Cloud Data Flow. But how big is that data? Well, we can see by running a query that it's about 169 million rows. Is that big data? I don't know. But one of the underappreciated facts of big data is that it starts out small. It starts out when you start streaming your logs, or start collecting your customer data, or you launch a new service. And you want to pick an analysis service that can handle data of any size. One of the great things about BigQuery is that it's scale invariant. So here is a query over 1 million rows of Wikipedia data that runs a regular expression over each row and aggregates by language. As you can expect, it doesn't take very long. 1.7 seconds. Of course, a million rows isn't cool. You know what's cool? A billion rows. So that only took another 2 seconds, but it did 1,000 times the work. But a billion rows isn't that large either. At some point, you've got 100 million customers and you want to track them each over 3 years. That's 100 billion rows. Let's see how BigQuery handles it. This is running 100 billion regular expressions over 4 terabytes of data. 6.2 seconds. If you wanted to do that in serial, it would take 32 hours to run that on a single CPU. A single disk would take 15 hours just to read it. So let's go back to the live stream of data from our music players. We can combine this with information that we already have to enhance its value. For example, we also have a table with playlists, which has track level information. Let's run a join query between these two tables to add a song and artist information. We can save this as a view so that we can think of this as its own table, but the values will be updated in real time since the input stream is also updated in real time. We might also want to give one of our partners access to this view, though they don't have access to the underlying data. We can do this by sharing the view dataset and adding the view to the ACL of the underlying table. Okay. Yeah, once we have combined these data sets, we can do something interesting with them. Let's figure out which artists are most popular for each hour of the day. We're going to use an advanced BigQuery feature here, the rank analytic function. Show here, which lets us find the relative ranking of each song by the hour. We'll pick the top 3. Note that this is using simulated data, which is why the Christmas song is so popular. Finally, let's use some real data to solve a real problem. If a user likes a particular artist, who else might they like? There are lots of approaches to this, but let's use the following. Given that people often put songs that they like together in a playlist, let's pick the artist that is most likely to follow our target artist in the same playlist. We can come up with a pretty simple query to do this based on the pieces we've already seen before. Let's say we're inspired by B.B. King and want to figure out who else we might like. So this says to try Eric Clapton, Bob Dylan, and John Lee Hooker. Not completely unreasonable. Let's try another one. What about Dr. Dre? Eminem, Snoop Dogg, 50 Cent, Tupac. Seems like a pretty decent recommendations with only a little bit of work. Now we've solved problem number 4, how to recommend music artists to your friends.